Thank you all for choosing to attend this talk today. My name is McNeill, and I'm really excited to talk to you about customizable probabilistic record linkage and to debut a tool called NameMatch that I've been working on for the last many years, and it just got open sourced last week. So really exciting and really excited to get to share it with you all today. So this is going to be our agenda for today. I'll start sort of by talking about record linkage more generally. Specifically, we'll go through what it is, why it matters, why we are trying to solve it with machine learning, and why it can be really difficult. Then we will sort of focus in on the NameMatch tool specifically. I'll go through what makes it special, what it requires, and how you can use it, and then we'll end with a full example. But before we dive in, I'll just give a little bit of background about me. So as was said in the intro, I'm a data scientist at the University of Chicago Crime Lab. The Crime Lab's mission is to design, test, and scale data science innovations to improve the public sector's response to the dual crises of gun violence and America's broken criminal justice system. So what our work looks like is that we partner with nonprofits and local government agencies to answer research questions using data. And so, as you might imagine, a lot of those projects that we do require record linkage as a first step. And so I have been at the Crime Lab for a little over 6 years now, all the while developing record linkage tools and using them to make our projects possible. And specifically over the last couple years, I've been working closely with Zubin Jelva and Eddie Lin to generalize these record linkage tools into the NameMatch tool, the open source tool that it is today. Okay, so what is record linkage? When I say record linkage throughout this talk, what I'm talking about is sort of the general task of figuring out which records refer to the same person within or across data sets. So if you imagine that we have these three data sets, record linkage could help us figure out that these three records all refer to the same person, and so on, so on, and so on, until all of our records across all the data sets have been associated with the other records that refer to the same person. And so after we've done record linkage, we have figured out that these four people exist in our data set. And not only do we know that there's four people, but we know exactly which records refer to each one of them. So why is this important? Record linkage is often a really critical prerequisite to many analytic tasks. And so that could be tasks like linking data sets together, deduplicating a data set that has multiple records per person that you want to collapse down to the person level. And then also a big one is the ability to understand a person's history over time. And this could really be any type of history, so you can apply it to whatever field you're in. This could be medical history, criminal history, purchasing history, voting history, really any type of situation where a person shows up in a data set over time because of incidents that have happened to them throughout time. Record linkage can often be really helpful in connecting those records so that you can create features about a person's history and outcomes about their future events. So I'm going to go through two quick examples to just really hopefully drive home the point that this is really valuable. And the first example comes from my own field. So program evaluation is something that government agencies, nonprofits, social science researchers like us at the Crime Lab often do to demonstrate the effectiveness of new programs or interventions in the real world. And so this often involves linking data sets to answer questions like which individuals from our study applied for public benefits in the next year, or which individuals in our study were arrested in the next 18 months. So you're often linking a study roster data set to some really large administrative data set. And then hopefully, again, this next example really hits home for everyone in this room because it applies to a lot of different fields. So any type of individualized prediction that you do, which this has kind of become a buzzword in the age of big data and machine learning, but whether you're predicting college acceptance or heart attack, rearrest, customer churn, if you have data that has events about people over time, then you're going to need to associate those records with a person's identity in order to build the features and outcomes that you need to do those prediction models. Okay, so now that we know a little bit about what record linkage is and why it's important, let's turn to talk about why we think we can solve it with machine learning. And I think the main reason for me is that at its core, record linkage is just a series of prediction problems that you're doing. So again and again, you're asking yourselves, do these two records refer to the same person? Yes or no? So we're looking at data and we're making a prediction if it's the same person or not. And another reason that this is a perfect task for machine learning is that the features that you would think about in order to make this prediction are really easy for a computer to understand as well. So to go through this example, we see a record for John Smith. We see another record for also John Smith, but no H in the name. And I think as a human trying to make this prediction, your mind would first go to like, okay, the first names have 1 character difference. The last names have 0 character difference. The DOBs are exactly the same. So these are like the features that we sort of start filling out in our mind in order to make this prediction. And computing the distance between strings is like something a computer can very easily do. And so after we observe these features, we might make the prediction that this is the same person. In this case, we see Taylor Brown and Tyler Browning. We can do the same thing. There's a little bit more variation here, so we might determine that this is not the same person. So after we sort of go through that process of creating features for each pair that we're interested in, we end up with a data set that looks like this, where we have a lot of different features, and that you're not limited to like first name distance, last name distance, DOB distance. There's like many different features that you can create for record linkage. So you'll have a data set with features, and then this same person column that is currently blank that we need to fill in. And so hopefully now that the data is in this format, it's starting to look very much like a machine learning problem. And so kind of stepping back for a second, like, why is this hard? So I've sort of framed this as record linkage can be rebranded as like a very typical prediction problem. So why is this so difficult? And after years of working on record linkage problems, I have come to the opinion that record linkage is very conceptually simple, but it's very operationally hard. And there's a couple of things that make it super hard. The first one is scale. So as we've sort of seen in the previous example, this prediction that we're doing is happening at the record pair level. And so if you imagine you are linking a data set with 1 million records, by the time you like blow that out to the pair level, you're in the space of like almost 500 trillion record pairs. So as you can imagine, it's very computationally expensive if you don't know sort of the right tricks to do, or if you're not super careful with how you do it. So that's the first challenge. And then the second challenge is that just because we know that we can think about record linkage as a prediction problem doesn't mean that we know how to generate these predictions. So a few slides back, we have these features, but we don't have any labels, and we might not have an intuitive sense of how to convert these features into that prediction. And so we're left with some tough questions. The first is what I just mentioned. How do you convert features or distance measures into a prediction? And then the second is, like, once you do make predictions, how do you know if they're good? This is often a problem because ground truth labeled data can be really hard to find in record linkage scenarios. And so this second question, like evaluating your process, you would hope could be easy, but often is not. And then the last question, say you do have some way of evaluating your performance and the performance is not as good as you want it to be. Is there anything that you can do about that? Like, is there a mechanism in the record linkage process or the tool that you're using that would allow you to make the performance better? So to demonstrate why those are such tough questions and to hopefully motivate why we think that the name match tool adds value, I'm going to walk through sort of the 5 most common record linkage approaches. So starting with the simplest, exact matching, this basically decides what a link is by saying if the first and the last name in the DOB match exactly, then it's a link. If they don't match exactly, then it's not a link. So obviously this is very simple and fast. So those are the pros. It can also it rarely leads to false positives. And so those are the pros of this method, but then conversely, like, because this is sort of a very basic method, we can end up with a lot of false negatives in this approach. So anytime there's a typo, like you're not gonna get it via exact matching. And the reason I say that there's likely false negatives is because, again, in this case, there's no ground truth labels, there's no model in sight, so we're really just guessing at the number of false negatives. We might sample our data and notice some, but there's really not a systematic way of quantifying the errors. And then there's also not a way to improve. If you happen to see that these 2 records have a minor typo and you want them to be linked, there's no way to make that happen via exact matching. So the next approach we'll look at is rule-based matching, which is basically where the user just defines every possible situation that could result in a link. So they might say, for example, 2 records should be linked if these 2 fields match, or if those 2 fields match, or if those 3 fields kind of match, and so on and so on. And so the benefit of this is that the user clearly has a lot of control in what's happening, but the downside is that it can be really time consuming because you just kind of can add rules to infinity as you keep noticing things. And again, so yeah, I say that in this method, you actually have the ability to make improvements, which is really important, but there's, at the end of the day, still no way to actually quantify the errors that you're making. So fuzzy matching is a really broad term, so I want to clarify what I mean here. In this context, I'm talking about fuzzy matching as when you have distance measures, you can kind of do a very crude way of combining them and then rank by that. So imagine that you just took a simple average of your first name distance, last name distance, and DOB distance, and then ranked your pairs according to that measure, and then kind of did an eyeball test and drew a threshold somewhere. That's what I mean by fuzzy matching here. And so again, there's no way, with no ground truth, no model, there's no way to actually quantify the errors that we're making via this process. You can kind of improve performance by tweaking the way that you're combining those features in some way, or by refining where you're kind of drawing that threshold, but you still don't have a ton of control and ability to know what errors you're making. So finally, we'll get into some probabilistic methods. So often when we want to build a machine learning model, but we don't have any labeled data, we are forced to turn to unsupervised methods. And so that's exactly what happens in the popular tool called FastLink. So here we use an algorithm like EM to estimate parameters in a model. Then we use that model to convert our distance measures into predicted probabilities. And technically, FastLink does output performance metrics, but because there's no labels, these are not performance metrics that are measured from the data. They're estimated from the model. And so they can be helpful, but you still kind of have to take them with a grain of salt a lot of the time. And then I say no in the improvement column here because I've had some experience using FastLink where, based on the characteristics of my data or based on how I set up the FastLink, the performance wasn't very good, and I didn't know, there wasn't a clear step for me to make it better because it's an unsupervised model. So lastly, we will look at active learning methods. This is the method that is used in the popular record linkage package called dedupe. And what happens here is that the algorithm finds pairs that it's really confused about, or it's having a really hard time making a prediction for. and then it prompts the user to label them, whether it's a match or a non-match. And then based on the labels that it gets from this process, it trains a model and is able to then predict or change the distance measures into predicted probabilities. And again, like FastLink, you do get performance metrics out of this, but because your ground truth data that you have is very limited in this setting, they're again like estimated from the model rather than measured from the data itself. And then you also do have some ability to improve performance using dedupe because, you know, the algorithm will keep giving you pairs to label until you decide that you're bored of labeling and want to stop. And so sort of the more time that you invest in that labeling process, the more ground truth you'll be giving it, and likely the better the model will get. So looking at this list, you can see that there's not really like one perfect solution to those really tough questions that we saw on the previous slide. And I would say like generally performance improves as you go down this list from sort of the very crude exact matching method to like getting more and more supervised in a sense as you go down. And so, but what we're really looking for in a record linkage tool is green yeses in the last two columns, where not only do we get good performance, but we can observe that performance and we can improve the performance if we need to. With that, we will turn our attention to name match and how we have tried to address those challenges. So starting with the basics, name match is a Python package and command line tool for probabilistic record linkage. I'm sort of going to spoil my own presentation by just cutting to the chase and sharing how we answer these tough questions. So in terms of how we convert features into a prediction, we do that using supervision. We train a model on labeled data, and then we use it to get predicted probabilities. And I'll show you where the labeled data comes from in a few slides. How do we know if the links we make are good? Well, because we have this labeled data, we can do a pretty standard evaluation procedure where we train on some of the labeled data, we evaluate using precision, we call AUC on the held out data. And then last, if you think that the links you make are not good, can you make them better? And the answer with name match is yes. There's several opportunities for customization in this tool. Sort of the most notable is the user has the ability to write Python that will be used to determine like what types of links are not allowed. So say the prediction model predicts that two records match, you can write Python to say like, if this is what it looks like, then that's an invalid match. And that can help improve your performance. So jumping back to the high level, what name match does is starts by taking in one or more data sets. Then we identify pairs of records that refer to the same person. We use that information to assign a universal person identifier to each record. And then lastly, we output the input data sets, but now they have this extra person identifier column attached. So the second step is really where all the magic happens. And so I don't want to gloss over it too quickly. I'll take you one level deeper into what's actually happening here. So this first step is called blocking. And what happens here is that we filter out a lot of pairs that are just so unrealistically like similar that we don't even need to waste the computational effort of looking deeper. An example of this would be if you see records with the name Melissa McNeill and Zubin Jelva, you can, once you see how different the names are, you don't need to waste time like calculating exactly how far the first name is, the middle name, the last name, the address. You can kind of just like set it aside and move on to the more complex examples. So after blocking, we are at the point where we can generate that prediction data set that we saw a few slides earlier. So we would have our distance metrics in there, like edit distance in the first name, edit distance in the last name, soundex difference of the middle name. You can really go crazy with whatever features you want. Once we have that data set, we will train our supervised learning model. And then finally, we will predict p-match, or the probability that two records refer to the same person, and set a threshold for what distinguishes a predicted match and a predicted non-match. So I also want to point out this third step because it can be really important too. So this third step is what we call clustering. And I think it's easiest to explain visually. So if you look on the right, if you think of each of those circles as a record, and then each line as a predicted link between those records, then you can see like the top three, there's three records. They were all predicted to be the same person. On the right, there's three records. Two of them, like two of the possible three pairs, were predicted to be the same person. But what we do during clustering is we identify the connected components in this network and assign them the same unique ID. So here you've seen, like, now the top three records are all referred to as person A. The records on the right are referred to as person B, and so on. So this is how we kind of do the very last step of getting that person identifier for each record. Okay, so as some of you may have guessed, based on the fact that name match requires labeled data, unfortunately not all linking tasks are going to be suitable for name match. There are two requirements in order to use it that we'll go through now. The first requirement is that all records have first name, last name, and some birth information, either like the full birth date or the birth year. And you can also have, address, phone number, middle name, race, gender. You can always include those in your link, but these are the only three that are required because of how much of the heavy lifting they do in the performance of our prediction model. So all of the records have to have that. And then some, not all, but some of your records have to meet these three criteria. So you have to have a ground truth person identifier that already exists in the data. You have to have people that show up in multiple records. And you have to have variation in the personally identifiable information that shows up across records. And so this second requirement might seem a little chaotic at the moment, but I think hopefully if we go through an example, it'll help. So here you see this data set meets the requirements because it has an existing ground truth identifier and social security number. It has people that show up multiple times. Here, SSN 123456789 shows up with two records. And then also important is when this person shows up multiple times, they sometimes have variation in their name. So once they are referred to as Jessica, and once they're referred to as Jessie. So we see now the structure of this that this requirement takes, but we still might not necessarily know why this is so useful. But I think to see, you can start answering these questions. So are records 1 and 2 the same person? Well, they have different social security numbers, so we say no. Are records 1 and 3 the same person? Well, they have the same social security number, so we'll say yes. So on, until suddenly you have ground truth labels that you can use to train this model. And so what does that actually get us? Now that we have labels, our machine learning problem becomes a supervised machine learning problem, which gets us higher performance relative to unsupervised and active learning methods. And very importantly, it finally gives us the ability to compute evaluation metrics for our linking process. Okay, so at this point, you might be thinking one of two things. One is that structure was so obscure, do you actually even see that in the real world? And it can be rare at times, but I can assure you that it does exist. So one type of data that very frequently meets this requirement is arrest records. And that's because, a person can get arrested more than once. They often have typos in their name or give a fake name or something like that. And then very importantly, anytime you're arrested, or at least in most jurisdictions, you're going to be fingerprinted and assigned a unique identifier. And then if you're arrested again, you'll get fingerprinted again and linked back to that same unique identifier. And so arrest records, based on those three criteria, almost always meet this requirement. The next thing that you might be thinking is, if your data already has a ground truth identifier, why do you need to do record linkage, or why do you need to use name match? That's a very valid question, but I think what we see often is that in data sets where ground truth is an option, like somebody had the option of filling in their social security number, it's often not required. And so you'll end up with a data set where like some of the social security numbers are filled in, but not all of them. And so you can use that to your advantage by using the records with social security number to generate this labeled data set that you need, and then use name match to fill in person identifiers for the remaining people that did not list their social security number. Okay, so I'll go through this quickly because I think I've already evangelized a lot about name match, but there's a few things that make it special. Ground truth requirement enables supervised learning and built-in performance evaluation. We have this ability for the user to define customizable constraints, which can help the user like encode logic that they have in their mind about like how records should and should not associate with each other into the name matching process. And then lastly, one thing that sets name match apart is that we have what's called like incremental mode, where if you say you already ran name match on 5 million records and now your partner comes and says like, oh, here's 1,000 more, like you can just add those 1,000 to the 5 million that you already linked, and that'll save you a lot of time rather than having to relink everything. Okay, so we're going to go into an example, but before that, I just wanted to walk quickly through the steps for actually using name match. So first, you fill out some configuration details, either in a YAML file or a Python dictionary. Then you have the option of writing these custom constraints in Python. Then you can run name match either via Python or the command line tool. And finally, you'll get a performance report output that you should review. So diving into this example, imagine we want to measure the impact of a summer mentoring program on grade point average and employment. Lucky for us, we have these 3 data sets sitting there. We have a program study roster, a school records data set, and an employment records data set. And our task is going to be to measure the average GPA and the average number of hours worked for students that did and did not participate in this mentoring program. So this is what our 3 data sets look like. The study roster is 1 record per person. The school records, 1 record per student per year per school they attended. So here you can see, there's the school, the year, the person information, stuff about their attendance and GPA. And then lastly, the employment records data set has 1 record per person per job. So you have record ID, person information, social security number, wages earned, hours worked, things like that. So always when we're considering using name match, the first step is to make sure we meet the requirements. So very quickly, we can see that we meet the first requirement. All 3 of our data sets have first name, last name, and DOB. To see if we meet the second, harder requirement, we can look more closely at our employment records data set. The first thing we notice is that we have social security number, which is our ground truth identifier. We have some people that show up more than once, Keisha Miller, Travis Smith. And then we also have some variation in PII. So Keisha Miller has a typo in her last name. Travis Smith has a typo in his DOB. That's going to be really helpful for training our model. So we do meet the requirements. And so we move on to the first step, which is to fill in this configuration file. So the first section of the config is where we define which data sets we want linked. So what you do is you kind of assign a short descriptive name for each data set. Here I'm calling them roster, school, and employment. And then under each of them, you just tell it the file path of where to find that file, and then the record ID column to use to identify records uniquely. The second part of our config is where we tell it which fields we want it to use during linking. So here we're just going to do 4, first name, last name, DOB, and ground truth. And so each little like chunk here follows the same format. You need to give the variable a name, which I'm showing now. Then you need to give the variable a compare type. And I think right now we have string, date, number, categorical. So what you put as the compare type will determine what distance measures are computed on that feature. And then the last thing that we need to do is tell it where to find this information in each of our files. So in the roster dataset, our first name column is in all caps. In the school dataset, it's called fname. The reason that we allow this is just to sort of limit the pre-processing that you have to do, so you don't have to like make sure all of your datasets have the same column names to begin with. And then the last thing to point out on this slide is this ground truth variable. So it has kind of this special compare type called unique ID. And this is where we tell it like, use this to build your training data. And then it's blank for roster and school because we don't have any ground truth in those fields. We only have social security number in our employment data. So every time you run name match, you'll have exactly one variable in this list that has that compare type unique ID. And then the last section of the config is where you can just define like more general parameters about how you want the linking to work. So here we're telling it like if you're going to parallelize, use 8 workers. When we have our labeled data, use 90% to train, 10% to evaluate, optimize the threshold based on performance, things like that. And then, so that's all that's required for running name match, but it's often a good idea to write these constraints. And so I'll give you a quick example. So say you ran name match and it comes back and tells you that these 2 records refer to the same person. You might believe them at first, you know, Jennifer Lee and Jenny Lee, they have the same birthday, that seems reasonable. But then on closer inspection, you realize that this poor person attended school for 464 days in a single school year. And this would be very hard for the computer to like know that that is not possible, but as a human, we can immediately see it and say like, I hope this is not real because that poor person attended way too much school. So what we can do about it now is add this chunk to this isValidLink function that's a part of name match. So what this function does is it takes in the predicted links, a data frame of predicted links, and it returns an indicator column for whether that link is valid. And so by default, you know, there's no constraints in this function, but then the user can start slotting in constraints here. So what we're showing it here is if 2 records have the same school year and the sum of their attendance days is greater than 365 days, set the valid indicator to false. And now when we rerun name match, it'll know to skip any records that look like that. One more example, this is 2 links or 2 records that name match told us were links from the mentoring study program roster, Mark Johnson. It's a common name, but like exact match, we would probably say that we agree, except for the fact that we know that our study roster already has 1 record per person. And so any link between study roster records should be invalid. And so in order to encode that, we just go back to this function, slot one more thing in here where we say if both of the records have dataset equals to roster, then set the valid indicator to false. Okay, so now that we have our config file all set up and our constraints written, we just have to run name match. We install it via pip, and then we can run it via the command line or run it via Python. Both cases are pretty simple. You're just like passing it the config file and the constraints file that you already defined. And then you run it and you'll get a lot of hopefully helpful log information. And then after it finishes, this is now what your data looks like. So it looks exactly as it did before name match, but now you have this cluster ID column appended. And this is the column that can be used as a universal person identifier across all of your data sets. So here you can see the 2 green records have the same cluster ID, and that's indicating that Jake Holloway in our program roster is the same as Jacob Holloway in our employment records. And then after you have looked at that, you can turn to the performance report. So there's two sections of this. The first is here where you kind of have standard machine learning evaluation metrics, precision, recall, AUC. All of these are computed out of sample on a small portion of our training data, or of our labeled data. And then the second section here kind of just gives you some key stats about how your input records became people throughout the process. So as you see here, we started with 22,000 records. We would have had to do 249 million possible pairs if we didn't have the magic of blocking. Instead, we only looked at about 31,000. We predicted that around 4,000 of them were links. Our constraints helped us eliminate 5 false positives, and we are left with around 17,000 people across all of these 22,000 records. So finally, we can answer our research question. And what we see is that the people who received mentoring have higher GPAs and higher number of employment hours than those who did not receive mentoring. So we're very excited. We have used record linkage to show that this mentoring program was a huge success. So I think I'm running out of time maybe, but I'll wrap up here. Record linkage, hopefully I've convinced you, is a really important processing step in many data tasks. It can also be very interesting and a very complex problem to solve. Quality matters a lot because if your record linkage is bad, then any type of analysis task that you're doing afterwards is going to be influenced by the errors that happened in your record linkage procedure. And so quality matters, and in order to make sure that quality is good and improve it, you need the ability to measure, to do this evaluation. With name match, you get the improvement in performance that comes with supervised learning. You also get built-in evaluation that comes with supervised learning. And then the user has a lot of control via these custom constraints that they can define. So we have some exciting work on the horizon, so please check us out and contribute. This is the link, and thank you.
Thanks a lot. I definitely learned a lot about record linkage and name match. I'm opening the forum for questions. Yes. Okay.
Hi. Have you ever looked at the stability of your matches? I imagine if you say person A is person B in this data set, then that precludes someone else from being matched to person B. So to a certain extent, the order in which you assign links matters. Have you ever thought about shuffling and seeing whether you result in the same linkages if you were to just match in a different order?
Yeah, that's a good question. So I guess one thing is, unless you have constraints that prevent multiple links, you're not going to preclude somebody else from linking to this record by linking to them first. It'll just be the case that all 3 of those records will refer to the same person. If you did have a constraint that said only 1 link per record, then you would definitely get into that problem. And by default, the links are considered in descending order of predicted probability. So, the idea there is that you're getting the best links first, and then up into a threshold. We have experimented with other orderings because in some projects, it makes more sense to do a chronological ordering rather than a performance ordering. And we haven't done a super scientific comparison, I guess, but generally I'd say it's only the links on the very margin that are going to be changed there, and it really matters how heavy-handed your constraints are as well.
Thanks.
First of all, thank you so much for sharing this. This is really impressive work. I work on similar problem, but instead of person, I do matching based on the business names. So my question was, since this is open source, can we use this, customize it, you know, build a completely different solution for based on business name match?
Business names. This is on our list of future things that we want to do.
Okay. Cool.
So right now, name match has been very like tailored to doing person matching. So all the default thresholds and the like the requirements of first name, last name, DOB are all tailored to people. But I think with a few minor tweaks, you could expand it to something like business names, and that's something we've also been curious about.
Great. Thank you.
So I have a question about the ground truth. For I think the questions that I'd imagine you'd be exploring, social security number seems like a perfectly established good ground truth to use. But for other domains that don't necessarily have that, I wanted to ask you, did you explore using any artificially created ground truths, or did you just use SSN because it was available?
Could you explain what you mean by artificially created?
So something really simple would be like a concatenation of like a couple different columns, last name, DOB, etc.
Mm-hmm. Yeah, so it's a good question. I think the problem with creating a ground truth indicator that's based on the features that you're going to be using in your model is you're going to end up creating like a deterministic mapping between features and the label. And so I think then the model would only learn the ability to encode the exact logic that you used to create the ground truth. And so we haven't explored that, but it does make it challenge. Like if you don't have access to this fingerprint ID or social security number, you kind of have to get like a little bit more creative with where you're finding your labeled data. Like in one case, we had student IDs, and it's really easy to find like examples of non-matches because it's like this record is probably not the same person as that record, just probabilistically. But it's really the ones that you have a hard time finding.
Do you get records about like name changes and stuff?
Yeah, so one big question we have is like what the fairness implications of record linkages, because you know it's more common for women to have significant name changes. When you do fuzzy matching, you're often looking for like, you know, 1 character difference or 2 character differences. If somebody suddenly has a completely new last name, then it can be a lot harder to link. In these cases, that's when like having address information or extra information like gender can be helpful in the link.
Yeah, I'm curious if the model takes into account commonality of names. I'd imagine that there would be a lot more false positives with John Smith than for a less common name. And if not, is there some other way to account for any demographic bias that might be introduced there?
Mm-hmm. Yeah, so we definitely do account for name commonness currently. So we have a measure in our features data set that says how often that name appears. And so like because we have that feature in our data set, the model can learn to, you know, use that information as is helpful. Earlier in the process, when we do blocking, we also factored in a little bit more manually. So we have thresholds for when record pairs get through the blocking process, and there we make the threshold lower if it's a really rare name and higher if it's a really common name, because the bigger your data set, say you're linking like every voter in the state of California, you know, there's going to be a lot of people with the same names, and you don't want that to generate too many false positives. And so that's another place where having more information like race, gender, address, phone number can be helpful to distinguish between the people with really common names.
Okay, I think we have time for one last question, and then we can wrap it up.
Oh, I was just gonna ask, can you share the picture of the GitHub link again?
Oh, yep.
Thank you.
Apologies to the others who have questions, and thanks a lot. Thank you, Melissa.